Bright Tuty. Every student matters.
The next thing that we'll be studying about is Kepler's laws. Now, Kepler, he made certain observations, and based on those observations, he gave 3 laws, right? The first law that he gave was that the sun is actually in between, and we know that the planets revolve round the sun. But Kepler said that sun is not exactly in the center. That means these planets are not actually revolving in circular orbits. They are not revolving in circular orbits. They are revolving in kind of elliptical orbits, and the sun is at the either of the two foci. Now, what exactly is meant by foci? When this curved part, if I take, we have studied about the mirrors, right, in 8th class. Then we know that there is a point which is known as focus. Similarly, for this curved part, this particular point B is said to be the focus. So, the sun is at either point A, this focus, or point B, this focus, and the plural of focus is foci, right. Some people pronounce it foci, that is one of the same thing. It is the plural of focus. So, one focus is A, one focus is B, right. Sun will be at either of these positions. It is not in the center. So, this is the first law given by Kepler. Now, in his second law, what Kepler stated was, he stated that, let us take an example. This is an orbit in which a planet is revolving around the sun. Let us see, the sun is here at point A, this focus, right. Now, he said that the line joining the distance sweeps a equal area. Let us take it with an example. You will not be able to understand just by the theoretical explanation. Let these points be x, y, z and p. Now, this particular planet is not actually revolving around the sun at one particular speed. It is changing its velocity, it is changing its speed, right. Fine. So, the time this particular planet takes to reach from x and y, right. So, for reaching x and y, this particular, by joining these 2 points with the part A or the focus where the sun is, we will see that this is the area swept by this planet. Now, when this planet is basically moving from y to z, so the area covered by this planet is this, and as per Kepler, this area, let it be A1, and this area, let it be A2, that will be equal. Now, indirectly, this particular statement, this particular law, indirectly we can assume that when the planet is near the sun, it moves a bit faster, and when it is far from the sun, it moves rather a bit slow, right, and in such a way that they cover an equal area. Got it? So, this is the Kepler's second law. Now, the Kepler's third law, which is quite important. Now, the third law that Kepler gave, he said that if we relate the distance, let it be expressed as small r, right, and if we take the cube of that distance, then this cube of the distance is directly proportional to the square of the time period in which a planet is revolving, right. So, t is taken to be the time period and r is taken to be the distance, right. So, as per Kepler's third law, this is Kepler's third law, which is quite important. As per Kepler's third law, r cube is directly proportional to t square. Now, we know that whenever we need to remove the sign of proportionality, right, and we want to make it equal, then in that case we need to multiply it with a constant, right. So, keeping the constant on this side, what we find is that taking r t square in the side of r cube, we get r cube by t square is equal to a constant. This is quite important that we need to remember, and we will be utilizing this third law just in the next topic. So, these were Kepler's 3 laws. I repeat the 3 laws. First of all, he gave the law that the planets are not orbiting in a circular orbit around the sun, they are in elliptical orbits, and the sun is not on the center, it is on either of the two foci. Second law, he stated that the area swept by the planet in moving from one point to another, that area is always equal if compared to the motion. Third thing, he said that r cube upon t square is equal to a constant. Got it? Now, let us relate one quite important thing, and that important thing is inverse square rule. Now, this inverse square rule states that f is inversely proportional to the square of the distances. Now, this inverse square rule, from where did it come? Let us see. It is based on Kepler's law, and let us see how we derived this particular inverse square rule. First thing, suppose the orbital velocity of the planet be v, it is denoted by small v, and radius of the orbit let us be small r. Then the force acting on the orbital planet will be given by F is directly proportional to v square upon r. Alright. Now, let us take it to be equation number 1. Second thing, if t we denote the time period taken by the planet to revolve round the sun taken to be capital T, then velocity v will be equal to 2 pi r upon t. Here we are assuming that it is a sphere in which the orbit in which the planet is moving, and we know that speed is equal to distance upon time. The distance measured will be in the case of circumference, and that circumference of that circular orbit is 2 pi r upon t, that is time period. Now, this is taken v is equal to 2 pi r upon t. Now, if we take the square of this v, this 2 and this pi, both are these constant values. So, we can say that v square is directly proportional to r square upon t square, because 2 pi is constant, 2 is a constant value, and pi also we know that the value is 22.22 by 7 or 3.14, which is constant. So, we can write it as v square is directly proportional to r square upon t square. It can once again be rewritten in this form, that I will multiply r in the numerator also, in the denominator also. It won't make much difference, right, because these if cut will remain the same. Fine. Now, if I try to equate it, what I will see is v square will be equal to r square into r. I can write to be r cube. This t square I have written as it is, multiply by this r I have written to be 1 by r, right. Fine. So, I can relate it like this. Now, as per Kepler's law, we have studied that r cube upon t square is equal to constant. This is what we studied in Kepler's third law, right, that r cube upon t square is equal to a constant. So, I can say that if this is a constant, then v square is directly proportional to 1 by r. Take it to be second equation. Now, if I combine the first equation and the second equation, what did we see in the first equation? That f is directly proportional to v square upon r. The first equation was f is directly proportional to v square upon r. Now, this v square from second equation of motion I can relate is again directly proportional to 1 by r. So, rather than writing v square, I can write here 1 by r divided by r. So, this becomes 1 by r square. So, F is directly proportional to 1 by r square. Now, this is an inverse square rule, right. It was deduced from Kepler's laws. Got it? Fine? Good. So, this is all about our planetary motions and Kepler's law and the Newton's law of gravitation. Fine? Now, there are one or two odd questions which we encounter in the examination based on this particular formula. Let us see how we calculate, right. Let us see an example. In this example, it is given to us that the mass of the earth is 6 into 10 to the power 24 kilograms. So, we are taking the earth as the first object and that of the moon is 7.4 into 10 to the power 22 kilograms, though the second object is taken to be the moon. So, let us see the information provided to us. Let the mass of the earth be m1 and that is given to be 6 into 10 to the power 24 kilograms. Let the mass of moon be m2 and the mass is given out to be 7.4 into 10 to the power 22 kilograms. If the distance between the earth and the moon is now distance denoted by small d is given out to be 3.84 into 10 to the power 5 kilometers. Now, one important thing that we need to remember here is while calculating these numericals, the masses will always be given to us in their SI units, kilograms, and most of the times the distance between them will be given in kilometers. So, this is the first thing students you need to remember while calculating the numericals, that we need to convert the kilometers into the SI unit of distance, which is meters. And how we are going to do it? We are just going to multiply it with 10 to the power 3 or 1000 to convert it into meters. So, now removing this kilometers, I can write that the distance is this much meters, right. Now, we need to calculate the force exerted by the earth on the moon. The value of G is given to us in the question, that is rounded off into 6.7 into 10 to the power minus 11 Newton meter square per kilogram square. Per, I have just removed that slash sign or divided by sign, I have just written inverse square. So, that is one or the same thing, alright. Now, all the values I have been given, I need to calculate or to find the force exerted by the earth on the moon. And as per universal law or Newton's law of gravitation, we know the formula for calculating the force. Force is given by capital G m1 m2 upon d square. Got it? We just need to put the values. All the values are given to us. Now, replacing these things with their values, rather than writing G, I will replace it with 6.7 into 10 to the power minus 11 multiply by the mass of the earth is given to be 10 to the power 24 and the mass of moon is given to be say 7.4 into 10 to the power 22 divided by the distance is squared up. So, the distance which is actually 3.84 into 10 to the power 5 into 10 to the power 3, I can just take 10 to the power 8, combining them both, and because it is the square d square. So, making the square, I will once again write it multiplying by 3.84 into 10 to the power 8. Now, students, these are very large values given in the question, and you people, you students, you tend to make mistakes while doing calculations. So, the first tip I would like to give you is, do not try to directly do this, rather just take it step by step, so that it should not be a mess all around while you are doing your calculations. The first step while calculating this formula and the force with this formula, the Newton's law of gravitation, the first step is, after putting the values, remove the decimals. Now, removing the decimals, this decimal is removed, I will multiply the denominator with 10. Removing this decimal, I will again multiply the denominator with 10, right. Removing the decimal from the denominator, I will multiply it 100 in the numerator, again removing this decimal, multiplying with 100. Got it? This is the first step. After removing all the decimals, now rewrite this particular value, and one thing you need to do in the second step is just multiply all the numeric values given, right, and take all the units of 10 to be together, right. Counting all the zeros together, what I can write is, just write 10 at one place. This is 10 to power minus 11 multiply by, this is 10 to minus 11 I have taken, 10 to the power 24, right, multiply by 10 to power 22 multiply by, this is 100 and 100, I can write 10 to the power, there are 4 zeros. So, I can write 10 to the power 4 here. Similarly, in the denominator also, I will take the numeric values except the powers of 10, I will write it at one place, then I will consider all the power of 10, like this is 1 0, including it with adding up the powers, 8 and 1 is 9, 9 and 8 is 17 and 1 is 18. So, I can just combine up the powers, writing it with 18, right. This is 10 power minus 11. Got it? Now, once again, rather than doing it directly, please write one more step. You are looking at it, if I am not putting these circles, which I am not going to do in my examination, there is no mess up, no cutting mess up being done over here, right, till now. Again 67 into 6 into 74 divided by 384 into 384. These are my values other than the powers of 10. Now, this 10 to the power 18, which is in the denominator, if it goes in the numerator, what it will become? 10 to the power minus 18, you already know. So, now keeping all the powers at one place, 10 to the power minus 11 multiply by, this 18 goes up and becomes minus 18, and now adding these two powers. These three are given to me. This is 24 plus 22, it comes out to be 46, and 4 it comes out to be 50. I can add up these powers 50. Got it? So, now I will take the 10 common in between, and if I add all these powers together, I find minus 11 and minus 18, which comes out to be minus 29 and 50. So, taking up, it will come out to be 67 into 6 into 74 divided by 384 into 384 multiply by 10 to the power 21. Look how simple it is, right. Now, I will calculate and cut off these values, and when I do it, I get it 0.201 into 10 to the power 21. If I take this decimal over here and I just shift it over here, in that case I can do it by writing 2.01, but by doing so I need to reduce one power, 10 to the power 20. You can write this or you can write this, they both are correct, fine. And since we are calculating what? We are calculating the force. So, the SI unit of force is, we know that it is Newton, represented by capital N. Therefore, we say that this is our answer, this is the force of 0.201 into 10 to the power 21 Newton, or 2.01 into 10 to the power 20 Newton. This is the force which is exerted on the moon by the earth, and it is this force because of which the moon is revolving round the earth. Got it?